Today, sir is going to deliver a lecture on analysis and design of buildings with RC shear walls. So, welcome everyone. And sir, now you may start.
Yes. So, good afternoon to all of you. Um, so, yesterday we discussed some of the basics of the capacity design philosophy in earthquake engineering. So, moving on to a slightly different topic, that is on reinforced concrete structural walls, or commonly what we call as shear wall. Okay, so we will try to see what are the different aspects one need to consider, what are the basic behavioral aspect as well as the analysis aspect. Okay, at the end I'll slightly dwell on the design part, mostly on the capacity design part. Okay, so very simple, so nothing to go into deeper challenge or so. And because the design part is mostly available in many textbooks, so the routine design steps I won't be discussing, because you can go through them and learn very easily. Okay, they are the same as any other reinforced concrete column or something like that. So let us start. So just let me apologize for the delay, because I was in some institute level meeting for some time. Somehow it got extended. Okay. Anyway, so let us move on. So this is the outline of today's presentation. So we will introduce the topic, then move on to the seismic behavior, and we will see what are the different types of failures observed in the past earthquakes, and then we will try to correlate that with the basic behavior, what we understand from mechanics point of view. Okay, because for any analysis of any structural component, whether it's a big tower, dam, or whatever, if you start from the mechanics point of view and try to correlate with the practical behavior, it is much easier to understand and it will be embedded in your mind. Okay, so always make up the habit of trying to understand from that mechanics or physics point of view. Okay, so we will discuss on that part. Then we'll move to the modeling aspect, and then I'll try to discuss some of the recent studies, what we have attempted, some numerical simulation, some experimental work, okay, in IIT Guwahati only. And there are many studies people have carried out and are still carrying out on different aspects of shear wall, but then we will try to get a glimpse of the main things. And then we will finally come to that seismic design, or in specific capacity design part, and then we will summarize. So let us move to the basic configuration and what exactly is shear wall. Okay, so typically we see most of our residential buildings or multi-story buildings in the urban areas, particularly in India, consisting of moment resisting frames. Okay, so in your moment resisting frame building, the typical elements all consist of the roof and the floor slabs, along with the vertical members typically as columns, and then you have the beams. Okay, so the beam column action and their uh, behavior make up the lateral load resisting mechanism. Right? They are the primary components. And then the slabs are the sources of the masses or the lumped weights. Okay? So together they uh, finally give rise to the dynamic behavior of the building. Right? And nevertheless, no less important is the role played by foundation. Foundation means the structural part of the foundation, that is footing or deep foundation like pile, and then we have the soil. Okay. So now the question arises, uh, when we have very large magnitude earthquake striking some of the structures located very close to it. Okay, the fault is very near to that. So the intensity of shaking experienced at that site is very high. Okay? So you'll have very large levels of ground acceleration, okay, and maybe permanent ground deformations. Okay, so in that context, whether these moment resisting frame buildings, whether they are sufficient or not, whether they can really cater to the stability and safety of the building. Okay, so your lateral force demand is very high. So whichever direction you consider, along the length or along the width, you take the action of these frames. So together they try to resist the lateral load. But then, since these columns and beams, they are not very large in cross section, so naturally their individual stiffness contribution is also on lower side. So beyond a certain lateral force or lateral force demand, these beam column frame system is unable to take care of the safety. Okay, so you need to enhance the lateral load resisting mechanism. So how do you enhance it? The best way is, instead of these columns, if you fill in the space between the columns by continuous reinforced concrete member. Okay, so how do you construct this? Starting from the footing, when you are constructing the columns, you make the formwork in such a way that together with these columns, the intermediate concrete part is also constructed. Okay, so this part, this element has small thickness, that is in cross section the thickness is small, however the length is large. So it is like a planar element, something like a slab in vertical orientation. Okay, so these elements are called walls, structural walls or shear walls, right? So these are having large lateral stiffness because when you consider the in plane direction, right, in the plane of that wall, okay, your effective dimension is the length and the width is the thickness. So when we look at the stiffness contribution of any member, we look at basically the second moment of area, right, I. And for rectangular section, we know that it is proportional to the width and proportional to the cube of the depth, BD cube by 12. So here in the cross section, if at the plane of the wall, D is the length, B is the thickness. So even if the thickness is small, the length is large. So cube of that gives a very large contribution. So the value of I or second moment of area for the in plane behavior of wall is much more as compared to the column. So you have if you orient the wall along the width, so if there is any ground motion or shaking along the width of the building, okay, and you have large lateral force demand, this wall, by virtue of its large depth, is going to absorb the force, right? It provides large stiffness also, because once you have large lateral force, the building will also try to sway along the width. So the large stiffness of the wall will also try to resist the lateral movement. So it will be minimized. So both the lateral strength of the building along the width as well as lateral stiffness of the building along the width, both are enhanced by virtue of the large in-plane dimension of the wall. So the thickness is the width and the depth of the section is the length. So naturally it enhances the stiffness and the strength. So whenever you have high lateral force demand, we tend to introduce shear wall or structural wall to take care of the your strength demand as well as the displacement demand. So both are catered, both are served with the same element, right? So now later moving on to how your wall is going to take care of the lateral forces, let us look at the basic mechanism. So we know that during earthquake shaking, you have the ground acceleration, and the ground acceleration gives rise to the inertia forces at the different flow levels. Since the slabs are the locations of the lump masses, the inertia forces are more at the locations of the floor slabs as well as the roof. So if you look at the figure, at the different floor levels, your forces are generated. They are transferred to the walls, right? Because these forces will try to be get shared among the different structural elements. So among the columns and the walls. Now, since the wall stiffness is more, the wall will attract more force as compared to the column, right? So the principal share, main share of the lateral forces will be carried by the wall, lesser by the columns. Okay? So your walls get the forces at every floor level. Finally, they transfer to the footing. So through your bearing pressure and other mechanisms, they are transferred to the underlying soil. So this is how your lateral forces are transferred from the floor level to the wall to the soil. So once you know the mechanism, in case of buildings, as we have seen, the columns are having lesser stiffness, so walls enhance the stiffness and strength. In case of bridges also, the same analogy is applied. You have seen the bridge piers in the form of frame members, just like columns, okay, number of piers. So along the width, you have this framing action of the bridge piers. So if you want to enhance the strength, instead of frame type of pier, you provide wall type of pier. So you must have seen these type of piers in the different uh, structures carrying the metro lines or the flyovers, and where not, everywhere they are used. So primarily this wall type of configuration is used to enhance the lateral strength and stiffness. So as we have mentioned, our two principal attributes we have already discussed: large lateral strength and high stiffness. So these structural walls are also commonly known as shear walls. Why? Because they can carry large amount of shear force. The horizontal force will come in the form of shear force. Right. So now the question is, as we had discussed yesterday, in our capacity design or earthquake resistant design, ductility is a foremost requirement. It is required at any cost. So your structural walls also need to be ductile. Now, there is a common notion that unless the member is quite flexible, it is bending very easily, it cannot be ductile. Just like columns. Columns are slender, so they can easily bend. Okay. Walls are deep members. Their stiffness is large, so if you try to bend a wall, it will not bend that easily. So, can the walls be ductile? Okay, because the columns can bend easily, so they can contribute to ductility, but whether the walls can be ductile. Okay, so that question was uh, uh, researched by many people over the years, and then people have carried out different experiments or so. So depending on the reinforcement detailing you impart in the wall cross section, you can make the wall behave in a ductile way. Okay, so that has been also proved. Let us look at the lateral force displacement behavior, just a comparison. When you have an ordinary reinforced concrete frame, moment resisting frame, you have a certain stiffness, you have a certain maximum strength, and then deformation. Okay? So there is a limit of its capacity. Then you have special moment resisting frame known as SMRF, what we call in that IS 1893 part 1, special moment resisting frame. What is the speciality here? Why do we call them special? Because of ductile detailing. Okay, so as we can see, they are stronger, they are stiffer, stiffness is more, and they can carry larger displacement as compared to the OMRF, that is ordinary moment resisting frame. So this is for the RC frame part. If you look at the wall part, whenever you have a frame building, RC frame buildings with walls, right, then obviously your stiffness is increased manifold, as we can see. Okay? And then, as I distinguished, a wall can be detailed in such a way that it behaves in a ductile way. So again, you classify into ordinary reinforced concrete wall frame, where the walls do not have ductile detailing, and the special RC wall frame where the walls have ductile. The behavior is obviously different as seen here. The deformation capacity of the special RC wall frame is larger as for due to the ductile decay. Okay, so at a glance, this is a generic comparison. What is observed as compared to the different categories of frames and frame with shear walls. As the displacement is reduced, the lateral sway of the building is reduced due to the stiffness of the wall. Okay, your non-structural damage is less. What is non-structural damage? Suppose you have a building where there is a laboratory of chemistry department. So you have a number of beakers, then pipettes, glassware, equipments, so many of them. So if that particular story, that floor experiences large acceleration as well as sway, what will happen? Those unattached equipments which are kept loose on the table, they will try to fall down. So these are non-structural elements, and then you incur a lot of damages. Many of those glasses will be broken. There will be economic losses like that. So these non-structural elements will get damaged if the building or that particular story sways too much. So if you have a wall, of course, the lateral displacement is reduced. So your non-structural elements remain undamaged. We look at different configurations where we use the shear walls. The first one, what we are seeing here, hollow shear wall. These are also known as elevator cores or core wall. Okay, C-O-R-E, core wall. Because through this, your elevator or lift generally moves up and down. So around them, we tend to provide reinforced concrete shear wall. Obviously, we need to have openings at the different stools, okay, for access. So this is a very common use. Then you have different shapes of walls depending on the requirement of lateral load resistance. So in our previous figure here, the wall was only along the width. Along the length of the building frame, there is no wall. So if you have large shaking around the length of the building, this wall, okay, will not be effective. Why? Because in the longer direction of the building, you have the dimension of the wall as its thickness. Okay? So the stiffness along the longer direction of the building, that's the length of the building, is very, very small, because it becomes the out of plane direction for the wall, not the in plane direction. So in your out of plane direction, what will happen? Your stiffness will be proportional to cube of the thickness and directly proportional to the depth. So instead of BD cube by 12, it becomes DB cube by 12. Okay. So obviously the stiffness is very, very small. So in the perpendicular direction, this wall will not be able to resist. So now in a building, you'd like to have the stiffness of the wall contributing in both the directions. Okay. Why in one particular direction? So to cater to that purpose, we provide the cross section in the form of C or L or T. Okay, so whatever is the direction of the wall in the perpendicular direction, in that direction also there is some part of the wall extended. So in both the direction, it will be able to contribute. Okay, so these shapes are also known as flange shape, because if you look at the section, these small portions become the flanges and the longer portion becomes the web. Okay. So now, when you look at the wall cross section, as I mentioned, when you cast the concrete from the foundation, you put the vertical bars, you put the horizontal bars. So if you reduce the dimension, cross section dimension of this wall to very small value, it becomes like a column. Okay. So your horizontal bars become like the ties of the column, and your vertical bars are the longitudinals. Okay. So now when you have the typical cross section of the shear wall like this, okay, so you can have two possible cases. One is at the end, you may have the same width of the wall as the entire web portion. Okay, so the intermediate portion as well as the end portion, they have the same thickness. Okay, the other category is your ends may have increased thickness. Just like here, if you see, the web portion or the intermediate portion has smaller thickness. The columns, the two building columns, end columns, between which you had put the wall, they have larger cross section. So most of the times we encounter this second category of cross section. Okay. What is the advantage here? You have larger cross section available at further distance away. So when the wall is subjected to lateral force or the moment, the ends of the wall are subjected to that tension compression couple. Okay, so one part of the, if your moment causes tension on one end, it will cause compression on the other end. So if you pack the ends, the two ends of the wall, if you pack them with more and more steel, congestion of steel, so your moment capacity also reduces, because the available lever arm of these two ends is the maximum. Okay, so instead of putting more vertical bars in the intermediate portion of the wall, we tend to put more bars at the ends. That's the natural tendency of increasing the moment capacity. Okay. So once you put them, your boundary ends, they are then called as boundary elements. Even if you do not increase the thickness of the wall, okay, the end column is having the same size as the wall thickness, okay, then also we tend to put more bars at the ends and call them as boundary elements. Okay, so if you have larger cross section, sometimes we call them as enlarged boundary element. If you have the same cross section, we simply call them as boundary. So these are the two categories. Now you may have only one layer of vertical bars and a single layer of horizontal bar, or you may have two layers in both the categories. Okay, what is the advantage or the difference in behavior? Here, if you see a single curtain of steel in both the cases, the concrete here on either side is just like a cover concrete. You don't have any confinement, right? But if you have two layers, right, the intermediate concrete is somewhat confined between the horizontal bars. This is a cross section. So at different layers, you'll have the horizontal bar with some certain vertical spacing. So your confinement effect will somewhat get mobilized if you use two curtains or two layers of bars. Okay? So this one is preferable, and most of the time when we use shear wall in building construction, we use two layers of bars. Let us look at how the reinforcement looks like. So this is how the reinforcement looks like. This is the bar having the end in the boundary elements. These are the bars in the boundary elements, and the wall is having same cross section throughout. Okay. And these are your ties. So the boundary elements can have separate ties, just like columns. And this is how your configuration looks like. And then if you have enlarged boundary element, just like what we have seen, so this is one typical view. So before concreting, when they have put the reinforcement, yes. So it's quite obvious that the vertical bars are more congested at the ends. You can see more number of bars at the two ends as compared to the intermediate. So those were the two types of cross section with boundary elements. Now let us look at the classification of your walls. So as we had mentioned in last class also, yesterday's lecture, that we have two categories of wall primarily. One is the slender wall, the other is the squat wall. So slender wall has this height to width dimension, more than 2. Okay. Sometimes people say it should be more than 3 to have proper slender behavior. So they act like vertical beams, right? They are cantilever beams because in isolation the wall is like a cantilever. It can have the lateral load. Okay, and you, by virtue of its slenderness ratio, this aspect ratio, your deformation is more in bending as compared to shear. Textual deformations are more. This is one figure of a large slender wall which was constructed for testing. So this is part of some laboratory experiment in University of California at San Diego, USA. So they have a large area where they construct these specimens in outdoor, open area. Instead of in laboratory, they construct in open area. and then they do the testing. So it's a full-scale multi-story wall. That's why you can see all the access ways and so on. Compared to the slender wall, the squat walls have this H by W ratio less than 1. So they can be thought of as rotated deep beam. Okay, so this is the fixed end of a deep beam, cantilever deep beam. Okay? And then once you put the lateral load, they will have the shear deformation, the shear type of behavior. So the conventional bending moment, the flexural design will not be applicable in case of squat walls. So most of the time we see our bridge piers and bridge piers in around the low height of the rivers or in urban areas, flyovers. Okay, most of them are squat in nature. So this was one figure, the wall type of bridge pier with squat configuration. So once we know the basics of the different components, let us look at the seismic behavior. First, let us look at the different modes of failure which were observed in past earthquakes. So let us look at the cantilever behavior, that is for slender walls. Okay, this was from an experimental observation, okay, the laboratory test which was carried out in some other university. So as you can see, they had boundary elements which were enlarged at the ends, and then it was simply tested under flexion, and then you had the flexural cracks in one direction, and then you had the compression concentration at one end. Okay, so this is the flexure shear behavior, just what you observe in case of a cantilever beam. Same way. Okay. You'll have tension cracks and then compression crushing. When you have large amount of compression, okay, the same type of behavior, when you have large amount of compression, what happens? You have the wall at different levels from the floors, the lateral forces are coming. So at the bottom, you'll have the maximum moment. So maximum compression comes at the bottom. So your end elements or the boundary elements, they experience large amount of compressive stress. So what is the consequence? If you do not have large if you do not have the lateral ties spaced at sufficiently close intervals, okay, that large compression can lead to buckling of the longitudinal parts. Just like you can have the buckling of any column, okay, if you have large spacing of the ties, okay, your concrete will not remain confined. So that's what happened in 2010 Chile earthquake or Mole earthquake. Large number of boundary elements got this type of crushing. So the concrete gets crushed. Sometimes the bending has been so much that the bar also had got fractured. This is very unusual, but still something has happened like that. Okay? So this is the result of large opening of the ties and those things. Then you have rocking type of failure. What is rocking type of failure? Your wall may be on this shallow footing, and along with this flexural cracks, if it happens that the underlying soil also undergoes some failure, so what can happen? The wall itself can rotate to some extent like a rigid body rotation. So if there is a reversible force or reversible movement, just like during an earthquake shaking, your wall can rock to and fro, okay, just like a rigid body rotation. So what will happen? You may not see more damages here. Some initial cracking may have happened, but later on you won't see that much of crushing or other damages as observed in this figure. But then the underlying part will get damaged. If you excavate and see the condition of the soil or the footing, definitely you see damages. Okay. So this type of failure is not so common in the conventional structural walls, but nowadays people are trying to construct shear walls in such a way that they allow this rocking type of movement only. They won't allow any other type of damage. They want only rocking type of movement. So rocking shear wall is also now being attempted in research. Then you have out of plane instability. What is out of plane instability? If you have the thickness of the wall or thickness of the web very small, So what will happen? You have large compression because you have a multi-story building. So from the top, large compression is coming. So towards the bottom, the compression may be so large that the wall may buckle in the out of plane direction. So the instability is arising in the out of plane direction. It can also get aggravated if the concrete is cracked. If the concrete is cracked, these sections have become weak. So the wall can bend in the out of plane direction because in the in plane direction it is very stiff. So whatever can happen is in the out of plane direction. So as you can see in experiments, they have also increased the compression and observed such failure. In reality, also that has happened. Again, if you look at these two pictures in Chile earthquake, you can see that this bottom ground story portion of the wall has undergone that type of out of plane instability. So such a nice type of deformation is rare, but then probably the estimated compression was less, okay, and whatever compression actually came was much higher. So the design was efficient. Now, this is the most interesting part. Generally, when we carry out the earthquake resistant design of any reinforced concrete frame building or with and without shear walls, generally we are not concerned with the damages in slab. We'll see later also that how slab can also get damaged when it is attached with the wall. Okay? Because yesterday I had mentioned that when the walls try to bend or sway during the earthquake shaking, at different flow levels, the slabs try to restrain. So at different flow levels, there is sharing of stresses, sharing of forces between the wall and the slab as well. The inertia forces are generated in the slab, they are transferred to the wall. But at the same time, there is some redistribution also. So the junction part can get damaged. That's what has been observed in case of one building, Chile earthquake. Okay. Let us come to some of the failure modes of squat walls. Sliding can be a possible mode of failure, as we had seen here. Now, in ordinary cases, conventionally, sliding is rarely like to happen because when you look at the bottom part, okay, unless you have some construction joint or already existing some weak plane, already the concrete is distressed, somewhat weak, then only there can be some relative movement. Otherwise, it is very unlikely that the lateral shear force can be so high to cause horizontal crack and then sliding. Okay? So, full sliding is very rarely observed. But then what we observe in squat type of walls or wall type piers is your shear failure. Okay? So, this has been observed extensively in past earthquakes. So, in 1999, there was this Chi earthquake in Taiwan, which is very famous for different reasons. So, one such highway bridge pier got sheared off in this way. Okay, so obviously the entire portion of this part of the bridge is unusable. So in squat walls, sometimes we try to figure out what can be the desirable mode of failure. Okay, as we know that whenever you have any element in shear, okay, there are two ways the shear can be transferred. One is the diagonal compression, and the other is the diagonal tension. Okay, so if you recall your solid mechanics background, you take an element, you apply tau on all the four edges in the complementary way. So you always get this diagonal actions. So now, whenever you have this diagonal tension in the concrete, it is going to cause cracks. So when you have diagonal tension along a particular direction, the cracks are going to appear in the perpendicular. So along the direction of diagonal compression, you will have the cracks because the tension is in the perpendicular direction. Now, all these walls have vertical bars, they have horizontal bars also. So if you have large cracking, obviously wherever the concrete and the steel is losing the bond, the steel is likely to yield. Okay? So in squat walls, we frequently face the question that whether the vertical bars should yield first or horizontal bars should yield first. It is not yet answered. Okay, so people are still trying to find out that what is the best mode of failure, desirable mode of failure. And then in some cases in the past, we have seen entire building with walls undergoing rigid body type of rotation, as we had seen here. But whenever you see this type of failure, that means the underlying soil is the main culprit. Okay? Unless the soil has undergone something, your this type of phenomenon will not be observed. Niigata earthquake is very famous, 1964 Niigata earthquake, because that was the first time extensively soil liquefaction was observed. Okay, so Niigata earthquake was very famous on that, and all these failures happened wherever you had this liquefaction, lateral spreading of the soil. Okay, the soil becomes weak, one part settles, it becomes somewhat asymmetric in nature of the load behavior, and then it caused the tilting. So when we look at the behavior of walls on frame buildings in past earthquakes, the different earthquakes experienced in the country of Chile, they have been of very much importance. Okay, why are they important? Because Chile is a country where they had been constructing these shear walls in buildings since quite a few decades, and their earthquake design code is quite advanced in terms of this wall detailing, wall behavior, all these clauses. Okay? So that's why whenever we look at the different wall design provisions, the Chilean code, okay, comes very handy. And they have been revising also, looking at the different observations of past earthquakes. They had seen that. So two Chile earthquakes are very important. If you look at the evolution of the structural design provisions of walls, one was in 1985, the other was in 2010. Okay. I don't remember, probably 2010 earthquake was higher in magnitude. It was 8 plus. Okay. But then there were many buildings which survived or which did not collapse due to the presence of walls. On the other hand, there were many buildings where the walls themselves got so severely damaged. Okay, so that was a cause of concern. So anyway, all these failures help us to learn and insight. So in both the earthquakes, the highlighting feature was that the slab wall junction, the floor slabs, they experienced a lot of damages. Okay, so somewhat people had overlooked that earlier and had the notion of the slab remaining undamaged, but these earthquakes opened the eyes. Okay, opened our eyes. So having gone past the different modes of failure, what we had observed, let us look at the basic actions, okay, the basic behavior part. So as we had seen earlier, your ground deformation gets translated into lateral forces in the form of inertia forces during shaking, and those lateral forces are transferred to the walls. So whenever we look at the forces and moments for the design of wall, okay, we try to isolate them, see how much force is coming, and at different locations at the floor levels, we try to find out our axial force, shear force, bending moment, and then we try to use them for design. So it is just like any other vertical load resisting member like column. But then when we look at the behavior in a slightly zoomed in or microscopic aspect, we land up in two different regions. So many of you may be knowing about this. So one is the B region, other is the D region. Okay, B stands for Bernoulli, okay, the famous person, and D is for disturbed. Okay. What are their characteristics? In any reinforced concrete member which is under loading, okay, you can identify B and D regions. So the simplest example is if you take a cantilever beam with a vertical concentrated load at the tip, okay, you expect a bending deformation, nicely bent with tensile stresses at the top surface and the compressive stresses at the bottom. Now what happens is whenever you have the material idealized in that linear, elastic, homogeneous, isotropic behavior, we tend to use the beam bending equation to evaluate the bending stresses. Bending stress sigma equal to my by I. Okay. So this is proportional to the bending moment, and along the depth of the section where you are evaluating the bending stress, that is determined by that small y, and you have the second moment of area as the denominator. Now that equation is applicable with all those underlying assumptions in a particular region of the beam. Okay, the shaded region in pink, that is where you have that equation strictly applicable. Whenever you come near the support or near the applied load, you will see that if the observed stress is not going to satisfy that equation, because there the stress distribution is not uniform. Okay, your strain distribution may not follow that linear profile what we assume. Okay, so all those give rise to certain disturbances or deviations from that beam bending stress equation. So those regions are called disturbed regions. Although we use that sigma equal to my by I to evaluate the maximum bending stress, and that is right at the support, okay, right near adjacent to the support. But still, truly speaking, that equation is not applicable. So these are the characteristic. In B region, you have that linear strain distribution, plane sections remaining plane before and after bending. All those are valid. Whereas in disturbed regions, you may not have linear distribution and you cannot do sectional analysis. So how do you analyze the D region? Best way, if you can carry out finite element modeling, okay, and look at the microscopic behavior. So just like other reinforced concrete members, you can have D regions and B regions in walls as well. Okay. So if you have a bridge pier means all the horizontal forces are at one level only along the height of the pier. You won't have the lateral force, okay, unless you are, obviously, if it is a tall pier, you are concentrating the entire mass at its center of mass, then you can think of an individual force at that intermediate level. But otherwise, you'll have a single force, and that causes D regions at the two extreme ends. Whereas in the building, when the wall has attachment to the floor slab at the different levels, at each of these levels, forces are transferred from the floors at different levels. Okay, so all those regions will become D regions, and you get very small region, intermediate position as D region. So you can imagine that if you consider this as an isolated cantilever wall, and at any section you just simply apply that equation sigma equal to my by I, you may not be looking at the true stress values, okay, the real stress values, okay, because the B region may be very small or may not be existing at all if the story is very short in height. So these are for the slender walls or wall type piers, and then you can have the squat configuration also. There also you will have D and B regions, but then if you look at this type of bridge pier, the entire region becomes a D region because the height is very short. So why are these regions important? Generally, what we have is our slender wall is a cantilever member, and then maximum bending moment is at the bottom. But if you consider this as D region, your maximum bending moment, which should be considered from the flexural behavior, will be here. That means at the end of this B region. And here it is like becomes a deep member, because if you look at the aspect ratio of only this part of the geometry, your distance is small, the length is small, or height is small, this dimension is small. So this is like a deep member. So here you have that strut type of mechanism, strut and tie model. So this is how the actual behavior should be analyzed. But right now in design codes and in general understanding also, we all use that sigma equal to my. So these can be the possible areas of research. Somebody can investigate further and come up with the strut and tie model here. Already people have tried to evolve those things. Okay. Similarly, for squat wall, we do not have any such strut and tie model. You open the design guidelines of the road bridges in IRC, Indian Road Congress. You look at the pier design, how it is designed. Every pier, irrespective of whether it's slender or squat, it is prescribed that you use the bending moment or the flexural behavior. But in squat wall type of piers, what we see extensively, that is not applicable. Okay, somehow we do not have failures, and these observed bridge piers are behaving in a desirable way. That's why probably we are not investigating further. But in reality, whenever you have squat type of pier, you will have these type of force transfer through struts. So you will not have that type of bending moment or bending. So all these I'm saying because this give you some idea that how the basic physics or the mechanics works. Now let us look at very interesting thing, that is how the cracked section of any RC member, here we are talking about walls, how the cracked section behaves or resists the shear. So let us take a slender wall where already the cracks have occurred in concrete under tensile stresses due to the bending. And then if you zoom in at one level, this is how the crack has propagated inside the section. So this is the crack tip. So you have a small portion of the concrete which is under compression. So the tip of the crack basically gives you the location of the neutral axis, okay? Zero stress. And then as you can see, the crack width has increased, and towards the tensile end of the section where you have the extreme tensile stress, your portion of the bar also has become unbonded with the concrete. You zoom in another level inside. So here you will see that how the entire shear force is getting resisted. Because whenever you have the shear force and the bending moment, it starts with the bending cracks, flexural cracks. But then after some time, the shear cracks also start, right? All of us know that if you have a rectangular section or any section and you apply a shear force, your shear stresses are the maximum in the interior part, the centroidal region. Okay? So your shear cracks, the diagonal tension crack, will start from that interior part. So the shear crack starts from the interior part of the section, flexural crack starts from the exterior, they merge, they become the flexural shear crack. Okay? And then it propagates more easily. So now, if you look at just the upper part of the section, you have these reinforcing bars bent. Okay, why? Because there must be the deformation compatibility. Once this crack width widens and there is a relative movement, this part of the wall tries to move with respect to the other part. Now these bars have to bend in order to accommodate that deformation or that movement. Okay? So all these bars tend to bend, right? And then towards the crack tip, where you have the two surfaces, crack surfaces very close to each other, you an aggregate interlock, right? The friction of the aggregates, because the surfaces are rough. In this portion, the surface is very rough. And then you have the compression region. So the entire shear force at any section, at this section, the crack section, will be partly resisted by this shear in the compression region, uncracked region, through this friction between the aggregates, aggregate interlock, as well as these resistance of the bars. So the bending of these bars is known as dowel action. Okay, all of us have heard about dowel bars. Where did you hear them? We have used dowel bars in case of pavements. You have two concrete slabs or two concrete pavements connected by dowel bars. What is their function? Their function is to accommodate movement, thermal movement or any type of movement. Okay? Relative movement between the two blocks. The same analogy is applicable here as well. Okay, that's why we call this action as dowel action. Dowel action is steel bar. Now these steel bars are very stiff. Okay? Basically, if you look at the minimum diameter of the bar, in column it is prescribed as 12 millimeter, the steel reinforcement. Same criterion is applicable for walls as well. So the minimum diameter is 12 millimeter. So 12 millimeter bar, if you try to bend like this, it requires quite a lot of effort. If you go on increasing the bar diameter, it becomes very difficult to bend, right? That's why larger diameter bars, you cannot do the bar bending manually. It needs machine. Okay, so this dowel action also helps in uh, resisting that sliding movement to a considerable extent. People have done research. If you look at classical textbooks on reinforced concrete like White and McGregor and others, people have done a lot of experiments to see the shear. How much is the aggregate interlock going to resist the shear? How much is the dowel action going to resist? Okay, so these are very important because in case of column, the depth of the section is small. Okay, but in wall, your this dimension is very large. So in the in plane direction, whenever you have this crack, these number of bars, the vertical bars, and so which are going into dowel action, that becomes very important. Okay. And these actually help in getting the guideline how much ductility this crack section can generate. Because all of us know, yesterday we discussed that whenever you have under reinforced behavior, your steel is going to yield, right? And then you'll have the damage, energy dissipation. It helps to travel the large deformation range, right? And gives us the ductile behavior. So all these are indicators to ductile behavior. So starting from this basic shear resisting mechanism, it's very important that how it can. Now, the very important part is the extent of this uncracked region. Okay? Because if this uncracked region is very small, that means this flexural shear crack has traveled almost the entire depth of the wall. Very small amount is remaining uncracked. That is not desirable because we should not have shear failure, right? Because if shear failure happens, our capacity design philosophy is not getting followed, right? We do not want shear mode of failure. So anyway, they are these are different issues one need to keep in mind, right? So this is how the shear is resistant in walls. So these are some of the basic aspects apart from the normal shear force bending moment, micro level aspects. Let us now look at the different modeling aspects. Okay. Okay. So till now, any question from the participants? Anything if you wish to ask? Let us take a break of a couple of minutes and then ask any question.
Sir?
Yes.
Hello. Yeah. Sir, I just wanted to ask that you told that disturbed region and Bernoulli or what? Yeah, that
Bernoulli
region.
region and disturbed
Yeah,
region. Yes.
disturbed region. So how do we decide that disturbed region means what, up to which, what distance it is disturbed region or undisturbed or Bernoulli region? Yeah.
Okay. So generally, if you look at a typical beam, reinforced concrete beam, this extent of D region from the support, okay, is approximately same as the depth of the beam. Okay.
Yeah.
So this is the rough guideline. If you look at the region near the load application, where the load is applied, generally this extent is say d by 2 to d by 3, something like that, where d is the depth of the beam, right?
Okay.
So this is for a general beam, okay, where you have the flexure deformation. So then if you uh, map it into the wall, because you just make a cantilever beam, rotate it horizontal, it becomes a slender wall. So here also, if you have the length of the wall as say L or LW, whatever, so this extent of the D region from the bottom support of the wall will be again approximately that LW or the length of the wall.
Okay.
So this is roughly the distribution. But then what happens is when you look at the uh, slab wall junction, when you have the wall connected to floors at different levels, that type of approximation does not hold good. Okay? So here it is very difficult to figure out that what exactly is the extent of D region, because it depends on the story height, the distance between the two floor levels. It depends on the length of the wall. It depends on the relative stiffness. There are many aspects. Okay? So when you consider a wall attached with slabs, it is very difficult to get the D region. But in case of beam, or if you consider wall in isolation, that from the support a distance of D or around the load application point, D/2 or D/3, that is sufficient.
Okay. Sir, one more question. Mahendra Kumar is asking, what is the effect of position of shear wall in RCC buildings?
What is the position?
Yeah.
Okay. So let me go back to this figure. So if you see the location of the wall, ideally the wall should be provided symmetrically. Okay, that means if a wall is provided along this end, along the width, a similar wall should be provided at the other end or at some intermediate location, so that mostly your distribution of stiffness is symmetric. Here what will happen? If you are providing wall only at one end along the width, and at all other frames along the width you are not providing any wall, what happens? There is a concentration of stiffness at this end. So whenever you have any earthquake shaking along the width, the forces are along the width. So that time what will happen? This part of the building, or this end of the building, will be very stiff. It will try to remain in position. As compared to that, the flexible part of the building, that means these frames, will try to move. So you will have a twisting behavior coming up in case of this type of configuration. That is detrimental, because twisting means these frames will be subjected to additional shear force. So that type of asymmetry in stiffness caused by the position of wall at one end, okay, that should be avoided at any cost. So we try to provide the walls in a symmetric way, okay, along the length, along the width. Okay. So that is generally kept in mind. If you are providing the elevator core wall, okay, that also we try to provide in such a way that we have two elevator cores at two ends of the building, or one at the central location, whatever. But then at the end of the day, you have to see that your position of walls should not cause sting effect or any unwanted force or movement which can be detrimental. Right. So symmetry is the key for positioning of shear.
So, question.
Yes.
Nitin Sharma is asking, what is the thickness, minimum thickness of wall? How do we decide that?
What is the minimum thickness of wall?
Yeah.
Okay. Generally, you have two possibilities, as I had mentioned. Yes. So there are two possibilities. You can provide a single layer of vertical steel, single layer of horizontal steel, or you can have two layers of vertical steel, two layers of horizontal steel. Now, what happens is, if you have a single layer, okay, it is prescribed to have a minimum thickness of 150 millimeter, okay, 150. That is prescribed in Indian Code IS 13920 and in other guidelines as well. Okay. However, when you are providing two layers of bars, your minimum thickness should be 200 millimeter, because you can very well figure out that if you want to provide two layers of bar, okay, what is the required minimum thickness? Say you take the nominal cover, right? Nominal cover for your wall as 40 millimeter. So two layers of bar means 40 millimeter, 40 millimeter, 80 millimeter on the two sides. Then you take the minimum thickness of bar or diameter of bar, 12 millimeter. So this horizontal layer of bar 12 millimeter here, similar 12 another two vertical bars of 12 millimeter. So 40 plus 40, the two nominal covers take you 80 millimeter. Then 4 layers of bars, 48 millimeter. So 128 millimeters is gone there. If you want to keep this thickness as 150 millimeter, you have only 22 millimeter left. 150 minus 128 is 122. Okay, so only 22 millimeter is not sufficient for concrete, right? Because when you are going to compact the concrete, you have to place the vibrator needle. It's not possible. Anyone who has seen concreting, it's not possible. So you need a minimum gap. Okay, so if you provide 200 millimeter, so 200 millimeter will give you another 50 millimeter. So around 72 millimeter is obtained in the intermediate part. Generally, vibrator needle you can have 55-60 millimeter onwards. The needle, different needles are available. So you can accommodate a needle inside. So 2 layers of bars, both for horizontal as well as vertical ones, they are prescribed. In every practical construction of shear wall, we use 2 layers of bar, and for that we use minimum thickness of 200. Okay. Generally, in shear wall, we try to provide minimum thickness or the thickness as small as possible for the wet part, the intermediate part, because this is the longer one. The end ones we try to increase in size and pack most. That is always beneficial because this intermediate part is not going to contribute to the moment capacity that much. So we proceed with 200 millimeter.
Okay. Sir, one more question. Mahendra Kumar is asking, providing shear wall in L shape at all 4 corners of the RCC building is really good or what? Is it beneficial or what?
Is it beneficial or what? Yes, it is beneficial. So the first question which I answered, I mentioned that these walls need to be placed symmetrically. So if you want to place at the corners, that means you can provide the shear walls in this L type of configuration. So in all the 4 corners, you provide L shape of walls. So at all the 4 corners, you have walls along width, walls along length. Okay, so that's quite good. So that you have symmetry both along the width as along the length. Okay, so that is fine. We can provide.
Yes. So in addition to that, Ravi Pratap is asking, how do we decide location of shear walls in the structures? It's where to provide or what?
See, from functional purpose, if you have elevator core, you must provide shear wall along that. For say sometimes 5-story, 6-story building, these elevator cores, they have masonry infill walls also. Okay, it's not that always we provide concrete walls as for the elevator core, but then it's a good practice. If you have multi-story buildings and especially in earthquake-prone regions, seismic zones 4, 5, so you have to provide some wall around elevator core. You provide shear wall. Okay? So your architect should position the building plan should be made in such a way. Architect should also know that your elevator core wall should not give rise to any asymmetry in the behavior. So that is from the functional requirement. Otherwise, there is no as such guideline that where exactly to provide shear wall. You can provide shear walls in intermediate frames also. Like you have here, I have shown the shear wall at the end bay. Okay, you can provide along the intermediate frames also. In the inner frames, you can provide shear wall. Okay, along the length also. There is no as such strict guidelines.
Okay, sir. So, yes, sir. Then let's continue.
Let's continue. Yes. Okay. So let us now go into the modeling aspect. Generally, for slender walls, one of the most popular way of modeling is use the equivalent frame model. Okay. So what is equivalent frame model? In equivalent frame, we are replacing the entire shear wall or the slender wall by an equivalent frame member, okay, with some intermediate rigid beam attachment at the floor levels. What is the purpose? Whenever you have this type of wall or this type of planar element, area element, we tend to use shell element, okay, for modeling. Whenever we try to simulate through numerical modeling, we try to model using the shell element. Okay. Now you are going to design the building. In shell element, it becomes difficult to extract the output of the design shear force, design bending moment, design axial force in a quick way. Okay. You want to see the output and quickly find out the values at different sections, different heights, and accordingly you want to design. That is difficult in shell element, because in shell element output you get first of all either the nodal displacements or the nodal stresses. Okay, so for finding out the horizontal shear or the bending moment, you have to extract the stresses, then do some summation. So you take a particular section, you discretize it into shell elements, so all those nodes will give you the stresses. So along that particular cross section, you have to do the summation, take the moment, and get the shear force bending. So it's tedious, it's cumbersome. So in order to have that quick estimation, people thought that we should not use shell element, we should use a frame element, just like you have the frame element for your beams and columns. Okay. Because after all, we are interested in that PV and L, shear force, bending moment, axial force. So the wall is having the physical representation of this frame element. The cross section of the frame element is given in the same dimension as the wall. Sometimes when you have the wall with enlarged boundary element, it looks like an I section, we have seen. So you give the cross section of this equivalent frame as the same as the I section. So you give the cross section of this frame as that I section, and once you give the I section, your columns are also going into the wall, because in reality your wall and the two end columns or the boundary elements, they will act monolithically because you have cast them together. The concreting is done together. So your boundary element, those cross sections are also going into the I cross section what you are assigning for the frame element. However, since your wall has to bend like this, whatever movement, your floor level nodes should also follow the displacement of this center line node, because in reality is your wall, right? The entire wall, what you are seeing here, is being replaced by this frame element. So these peripheral nodes, these end nodes points, these should also follow the displacement or the deformed shape as the main frame member. So how do you achieve that? You connect this central frame node to the end node by means of rigid link. Rigid link means you assign any frame member, make the modulus of elasticity as very high, say 1,000 times or 10 to the power 5 times that of the concrete, whatever you are assigning for the beams and all. Okay, so for this frame element, you provide the modulus of elasticity compatible with your grade of concrete. Okay, 5,000 root FC or whatever you want to use. And for these rigid beams or rigid links, you make them very stiff, so that whenever this frame tries to bend, the peripheral nodes at all these flow levels, they will also follow the same deformed shape. Okay. So by analyzing this, then you provide the beams and the columns as frame members, you apply the design loads, and directly at different sections, you will get the design axial force, shear force, and bending. So this is a very popular model when you are trying to do the design of shear wall. Next comes your vertical line element model. There are different macroscopic models, okay, but then I'll discuss only 2-3 of them. What is this line element model? Whenever you have this wall, okay, any panel of the wall between two floor levels, one story, you have the bending behavior as well as the shear behavior. Okay, so the idea is that the bending behavior will be consisting of some tensile force and compressive force, that couple action. and you have the tensile force and compressive force coming through only those members. So for compression members, we have struts, tension members, we have ties, just like in a truss. Okay, so you can think of the boundary elements or the portion where you have the tension as having the truss elements with the ends as pinned. Here also they are the truss elements. If this is taking the compression, these become struts, these become ties, and vice versa, whichever way you apply the force. Okay, so these elements, what you are seeing as pinned elements, these take care of the longitudinal forces, bending forces, and the shear part is taken by this spring. Okay, so whenever you apply the shear, this spring should be able to take care of the action. So this is multiple vertical line element model. There have been different modifications on this also, TVLEM, and there are many other models. Okay, so these are fine as far as understanding the behavior is concerned. But then it's very obvious that if you ask a designer to apply this model, obviously the answer will be no. It's not feasible. So those are for the slender walls. Then coming to the squat walls. Okay. So in squat walls, as we had seen, that the bending behavior is not going to happen. So you have the strut and tie model. So whenever you have an horizontal force, it passes through this compression path known as strut. Okay. So you can have multiple strut in different ways, and then people have tried to figure out that you can have struts in this orientation, you can have strut in this orientation. So people have tried to understand and figure out the behavior of squat walls in different. And then once you have the concrete and reinforcement, you have to apply the material models as well. Uh, this is one variation of this model for squat walls. This actually came up from the deep beam. In deep beam, what happens? Whenever you apply a force, again the same concept, the span of the beam is too small as compared to the depth to ensure the shallow beam action or the flexural action. So the load transfer from the point of application to the supports are through direct compression path known as struts. So instead of single strut model like one member here, one member here, this entire grid for the member for the deep beam is thought of having the configuration of a lattice. Okay, so this is not so popular, but then just wanted to show you that how people have thought of trying this, and then they have tried to find out the different members which are having the different properties, okay, their behavior like that. Well, so those are your macro modeling. Now let us come to the micro modeling, which is the important part. So the first level of micro modeling is the fiber element. Okay, we are most familiar with the finite element modeling. So this modeling is an intermediate one between your finite element model and your macro model. So what is fiber model? Suppose you have a cross section, some flange cross section. So what we assume is that your entire cross section consists of different fibers. Okay. So if you have a wall like this, you have fibers running along the height of the wall from the top to bottom. Okay. So basically, in your cross section, you will see the different ends of the fibers at any cross section. So this is the typical one fiber, what is shown, and this has been zoomed in here. Okay. So you'll have such type of fibers along the length of the wall. Okay. What is the use of these fibers? These fibers are assigned the material properties, the stress strain curve. If you are doing monotonic loading, you give the monotonic stress strain curve. If you are doing cyclic loading, you get the appropriate one. So these curves are given as input, and you give the fibers. So as you can see, there is a kind of meshing. What is shown here? Okay, so this entire portion is meshed in a different way. So all these mesh spaces, they are the fibers. Okay? And then you can assign separate fibers for the reinforcing bars also. Right? So that can also be done. So these reinforcing bars are the steel fibers. So you assign the stress strain property for the steel, as you can see. These are the stress strain properties for the steel, a reversible loading case. And then you assign the fibers for the concrete. So this is a popular model because fiber modeling somehow takes care of the material stress strain properties in an appropriate manner. Okay. When you are doing the design, you are doing the linear elastic analysis, you do not need the stress strain property. Why? Because your modulus of elasticity remains constant, E. Single valued E does not uh, mandate this type of modeling. Unnecessary, this type of details are not required. So these modeling are generally not carried out in practical design firms, where you are only concerned with the design. But then, if you are interested to see the actual behavior and interested to see the extent of nonlinearity developing, how the failure can happen, you have to monitor the stress strain behavior. So for that, this fiber model is very important. So next is your finite element modeling. So this is quite common. And then when you do the finite element modeling of wall, generally we use 8 noded brick elements. Okay, and then brick elements can have more nodes also. 8 nodes are only at the corner ones. You can have higher nodes. So as required, you can change them. And then generally we use the truss elements for the bars, right? The advantage here is that in the boundary elements, as we have seen, that you provide the ties at closer intervals, you have more bars. So there is a certain confining action at the two ends, because it also helps your ends are subjected to more stresses. If you have more compression at the end and you confine the concrete, it actually saves the concrete. The concrete does not fail earlier. Okay, so those things can be mobilized here. So these figures are taken from one of the studies. My first PhD student, Dr. Snehal Kaushik, she analyzed this slab wall behavior, and then for some validation, she had modeled this. So this is the typical view if you model in Abacus. Okay, she used the 8 noded solid elements, and then this is the reinforcement mesh. At the ends, you have the boundary elements. She did not have enlarged boundary element. She had the same thickness. So this is how you can model. Okay. My current PhD student, one of my students, Somi Rajman, she's also modeling in the same way. Okay. And we followed the original study by Pantazopol and Imran. That paper actually showed us the details how we can model this. So that is for the modeling of the members. And then when you come to the material property, again, if you are interested in linear elastic behavior, you need not worry about all these. But then for nonlinear behavior, if you are doing in Abacus, the popular model is the concrete damage plasticity model, CTP. Okay. The advantage is that the strength degradation and the stiffness degradation both are taken care of. As we had seen, when we consider the ductility, we had mentioned that the strength should not fall down, right? The strength should be retained when it's traveling on that deformation curve. Okay? So the strength degradation as well as the stiffness degradation, they can be modeled quite comprehensively. So you can model the unconfined, confined concrete, as I mentioned yesterday in the lecture, and then the actual stress strain curve of steel with the strain hardening and the overstrength part, what we generally ignore. So then you have certain variables or parameters in concrete damage plasticity. You can have the values of different damage parameters. Basically, whenever you study some component behavior in Abacus or any finite element model, you need to validate your model. Okay? So for that, some fine tuning is required. You need to play around with the parameters. So the damage variables DT and DC, these are the most important ones as far as the extent of damage is concerned. Okay? And especially in concrete damage, it is a major aspect. These are the simplified material models which can be considered. You can use different properties of tensile stress strain curve also. Generally in design, what we do, we ignore the tensile strength of concrete. But then in nonlinear analysis, since there is some small tensile strength, it is better to take care of that also. So generally we consider the tensile strength of concrete as well. And then we apply the material model for steel. There are two forms in which the stress strain curve of steel can be given. One is the nominal stress and the other is your true stress. So the corresponding quantity on the abscissa, x-axis, that also changes. So you have to give these values a bit carefully, because finally your results depend on these values only. Fine. So with those things in modeling, let us have a look at the recent studies we are carried out. So this is from the work of Dr. Snehal Kaushik, what we attempted. So basically the behavior of floor slab and its influence in connection with the wall, right? So this was the building, what she studied. And since the area of interest was primarily the behavior of slab connected to the wall, so we did the meshing of the reinforcement and all the things in this part only. Okay, because the more you provide the details of your model and in a multi-story building model, it becomes very difficult for the numerical computation. The how fast your model can run depends on all these details. Okay? So the meshing of main reinforcement was primarily concentrated here, and we thought about a symmetric configuration with only the walls and no asymmetry in the building. These are the reinforcement details. So this was how the models looked like. So the intention was, if we isolate this model, like the wall and the connected slabs, and then we try to simulate the behavior, how far this type of modeling simulates the actual behavior of the wall and slab in the entire building. So this was our primary intention of the study, and then obviously to understand the damage also. So we attempted both types of models. Okay. So these were the portions of the floor slab with mesh reinforcement. Well, the analysis carried out was nonlinear static analysis. We are not showing the dynamic analysis results here. What I want you to see here is that there were two types of full building models. One was having lesser number of stories, one was having more number of stories. Okay. So these were analyzed. So we did pushover analysis, okay, and displacement control pushover analysis, so that the extent of the deformability and the extent of the lateral strength both are estimated. Okay, and then what we see here is this is a monotonic behavior, monotonic analysis, not cyclic. So the deform shape will tell us that on which side you had the primarily tensile stresses and which side you had the compressive stresses. So as you can see, if this had been a typical slender wall behavior, like an isolated cantilever wall, you would have got a large extent of tensile stresses on one face and large extent of compressive stresses on the other face. Okay? But here, what is observed is the entire wall is behaving like a composition of isolated story panels. Like for each panel, a certain pattern is getting repeated. What is this pattern? Primarily, this panel is like a squat panel because the height was around 3 to 3.4 meters and this length was around 4 meters, 4.5 to 5 meters. So this was squat panel. So the squat panel, the typical behavior is like a compression flow or strut, okay, not like the bending behavior. So that's what is exactly observed. These are the flow paths of the compression, and then we had the tensile damages at certain location. These were the tensile damage. This indicated the different levels of damage. Okay, so the strut type of behavior the entire wall getting distributed into different panels, squat panels. That's the key observation. So this is the influence of the floor slab. Unlike your isolated standalone cantilever type of behavior, where you have continuous regions of tensile and compressive stresses, you are getting repetition of certain stress distribution. So, in other words, your basic behavior of the slender wall as standalone isolated cantilever wall is not holding good when it is connected to floor slabs. If the floor slabs were absent, you would have seen that type of stresses. So the concentration of damage at the wall slab junction, diagonal strut formation, that's observed. So if you see the isolated wall also, there also we have that same type of flow of stress. Okay. So this model became sufficient to further carry out parametric studies. Okay. Exactly what we had mentioned, or we are trying to highlight, that the D region or the disturbed region is having some other stress distribution, unlike our general understanding. So that's what is observed. Each of these regions has become D regions, right? So as one of you asked that what is the extent of the D region, here you can see that the entire wall consists of D region only. There is no B region, nothing, because each wall panel is squat. Had the story height been very large, the length has been small, so each panel would have been slender panel, then probably B region would have appeared. But here they are not appearing. So anyway, this D region part still remains unsolved, but the numerical simulation at least reinforced that D region really exists. That part. These were the damages in the slab. Unlike the general understanding that the slab is not going to get damaged, the damages were observed in the slab. So these are the four parts of the slab, okay, where you have the connection with the wall. These are the portions where you have the walls connected. The damages were observed to be poor. Okay, and these are the different other parts of the panel. Okay, so these two figures refer to the portions of the slab attached to the wall directly. So that was the numerical simulation by Dr. Snehal Kaushik, and then currently one of my students, Soumi Rajbanshi, she's trying to see the extent of confinement, the boundary element of shear wall. So in her study, she had done testing of a slender wall in our structural engineering laboratory, and it was a tall wall because we tried to model it as close to one full scale model as possible. Okay, so it was more than 3 meters in height, okay, in total, and you can see this is the base beam, and this was the wall. We had the two reaction frames. We had put some nominal vertical load because we don't have that large actuator attachment to give very large vertical load, and this was also attempted for the first time, so we had to be very cautious. So we had put some nominal vertical load, and with the help of the crane we were attaching them. So this was from the other direction along the plane of the wall. This view is along the plane of the wall. This is the strong wall, and the bottom was our strong floor. Okay. So this was how the things were attached. So as you can see, it was subjected to cyclic test, okay, displacement control cyclic test, and then you can see the flexural cracks in the boundary element. Okay, this was with enlarged boundary element, and we can see the flexural cracks. And the interesting part is that the cracks extended to a large height. And as you come more towards the interior part of the web, they become diagonal cracks. So all of us know that the shear cracks are in diagonal direction, they are inclined direction. So the cracks what we see in the web, these are the shear cracks. These are the LVDTs, certain sensors to measure the displacements. Okay, and the diagonal configuration helps us to measure the shear deformation. Okay, so these are the different flexural cracks in the boundary elements. So this was a good test in the sense that at least we can see the shear wall behavior, how it behaves. Okay, what happens is, since it's a tall element, and we also restricted the out of plane movement by means of certain rollers. Okay, but still there was some out of plane movement, diagonal movement was coming, and higher displacements. Okay. So this is how shear walls get tested and give us a lot of insight. The strain distributions showed a lot of nonlinear variation. Okay, they were not linear strain distributions. So these were some recent studies on the behavior part. So let me focus on the seismic design, the basic aspect. Just to re-emphasize that whenever we do seismic design, we have to do the first stage limit state method, and then the second stage it becomes the capacity design. So the different load factors are also specified in the codes of other countries. I'm not showing the 13920 IS 1893 here. When you do the design, you follow the same IS 1893 part 1 load combination, your IS 456 2000. The conventional structural design is the same as we have discussed yesterday. Okay. And then when you do the capacity design, you have to use the actual stress strain curve. Okay. But your design stress strain curves also give us a lot of insight. So one of the major accomplishments in IS 13920-2016 was the removal of the superposition of the boundary element and web. Okay. Still, most of the times, your design of this boundary elements or the end columns are done as per the provisions of column design, IS 456 2000. Okay, so the basic design is done as per that, and then in IS 13920-2000 you have the special confinement reinforcement for the columns, as we had seen yesterday. So we follow the same provision for the boundary elements also. Okay. So now people tended to think that the behavior of the boundary elements and the wall can be disassembled and done separately and then superposed to get the actual capacity, right? So this was how the behavior used to be. Even in the earlier version of 1993, the behavior used to be like this. You know the total moment on the wall, and by assuming a reinforcement, you find out the moment of resistance for the rectangular section, the web part, and then you find that how much tension or compression is coming on the two boundary elements. But then, luckily, this has been removed in the 2016. Okay, and even the other codes from very early years, they were proposing that the superposition is not possible. You have to consider the entire section as a whole. Okay, so although this composite analysis is now prescribed in 2016 version 13920, still the reinforcement and other details are followed in the same way as the column in 13920. Okay. So I just wanted to highlight this major thing. And then when we move to capacity design, how do we do the capacity design? Just like we try to first estimate the actual material stress strain curve, and from there we try to get the moment capacity which gets generated during earthquake shaking, and then we try to see how much shear force gets generated. We had seen at the ends of the beam how much shear force was getting generated from the moment equilibrium, m omega. Okay, so if you consider an isolated wall, the shear force coming due to that m omega at the bottom will be given by this equation. And once you get the m omega, you find out the shear force, and then you can find out what is the shear capacity of this section, right? Shear capacity of the section, and it will be contributed by both concrete and reinforcement. You have the horizontal bars in the section. So these horizontal bars are the primary transverse reinforcement in the web of the wall. From there you will get this VUS, and VUC is the same as the shear capacity of the concrete. So that tau CBD, whatever we use for rectangular section, that is also applicable. All these are given in 13920. So you check the shear capacity, whether the shear design is safe or not. So when this moment is generated based on the actual stress strain curve, that m omega you have to consider. So these things I had partly studied during my MTech days at IIT Kanpur. So that's when I learned all these overstrength and other aspects. Okay. So this was a very good exercise. And finally, at that time also, we had done the sectional analysis. This is how you get the PM omega curve. We are familiar with that design PM curve as given in SP16, where you have this axial force normalized as with P by FCKBD. M is normalized as M by FCKBD square. So instead of that, this is not in the normalized form. So you can get the same way the M omega. That was for the design case, SP16. This is for the overstrength case. So what is the difference? For the SP16 curves, you are using the design stress strain curve. Here for PM omega curve, you have to use the actual stress strain. Otherwise, the procedure remains same. You have the variation of neutral axis along the depth of the section as you travel from the peak compression point down to the balance section and then going to the extreme side. Okay. This is the entire part of your PM interaction curve. What is then SP16? In SP16, you have two different figures. One figure giving the upper half, the first quadrant, and the second figure giving the fourth quadrant. So these are shown together. So when we find out that M omega, that is the major challenge, we consider two parts. Like when you have the section with enlarged boundary element, you have the confined concrete here, you have the confined concrete in the web, okay, because these horizontal bars are confining the concrete. So this is the total concrete area. You break up into that confined concrete and unconfined concrete. We are showing only the half portion, half of the section. So this part is the half confined concrete and this part is one half of the unconfined. So this is basically the cover concrete. What is? So you have to use the two different stress strain curves for that. If you are having single layer of reinforcement in web, your confinement in the web portion is gone. You have only the confined portion in the end boundary area. So these are all required when you find the M omega, because when you are finding the normal design moment capacity as given in the appendix of IS 13920, you don't differentiate between confined and unconfined. You use a single stress strain curve. So there are different models for getting the confined and unconfined concrete, the values of the stress strain, stresses and strains. But then Razvi Sasioglu model that time was very popular. So now also people use this model. So we had used these values, different values. So our design stress strain curve of IS 456-2000 is because it is obtained directly from the cube test, and when you crush a concrete cube, there is no confinement, there is no reinforcement, right? So it matches closely with the unconfined concrete strain. So that's how you land up with very close values. What we see, only our IS 456-2000 stress strain curve doesn't rise to FCK. It goes up to say 0.45 FCK, and then it becomes flat. Right? Anyway, that is idealized for design with the partial safety factor. So this was for concrete. This was for the steel. Some testing of the high strength, high strength deformed bars were done in the IIT Kanpur laboratory. So those values were used. So yesterday I had mentioned that this peak strength can go up to almost 1.25 FY, 25% more than the FY. If you look at the strain, it nearly reaches around 14-15%. That's very high. But then we never use these values because we are not going to use the actual stress strain curve in design. Okay? But then when we carry out the capacity design, talk about overstrength, we all use this. So using them, I had compared the difference between the design PM curve and the overstrength PM curve, right? So these are in the normalized form. Instead of B and D, I use the thickness of the web and the length of the wall. So these are the curves which are for the design stress strain curve. So this outer one is for the overstrength property, actual property. You compare this one with the outer one for the design. So you can see how much margin there is when you consider the overstrength. So that much increased moment is generated for a particular axial force. So that is M omega. So with this increased moment, your applied shear force is also high as compared to the design shear force compatible with this design PM curve. Okay. So these smaller ones are from the design stress strain properties. These lines with the larger thickness are for the actual stress strain. So that gave us a good insight that in real earthquake shaking, when you are talking about the overstrength of beam, column, wall, how much additional shear force gets mobilized, which can make the structure unsafe. If you have not given enough margin in the shear design, it can lead to shear failure. So this much for the capacity design, and the normal conventional limit state method design of RC walls you will get in reference books. I have mentioned the reference books. Examples are there. They are same way done for the columns. Okay, PM interaction curve and same way. There is no difference as such. Okay. So in closure, these are some of the future directions we should be concerned with. One is the slab wall behavior. A lot of design guidelines and whether at all plastic hinges can be defined in such cases, right? It may not be possible when you have that squat panel type of behavior, because plastic hinge zone means very demarcated regions of damage, okay, very clear regions of damage, which may not be possible to achieve in such cases. And then the soil structure interaction of RC frame wall buildings, because uh, not much work has been done on this. People have studied. So one of my PhD students has just completed his work on this. Let us see how things are. And then we need a lot of experimental investigations on shear walls. If you look at currently the research carried out on shear walls in India, it's very less. It's not sufficient. And especially on flanged walls with normal enlarged boundary elements is one aspect. And then with flanges, these are very common for elevated roads. So a lot of work needs to be done on these aspects. So these are some of the books what you can refer. So three of them are similar ones what I mentioned for yesterday. So these are the three books by Paul A. Priestley, Jack Muelle, and Agrawal Srikhande. Agrawal Srikhande has a solved example with IS 13920, but unfortunately it is with the 1993 edition. So most of the provisions are same in 1993 and 2016 version. So as such, the design calculations should not change. Okay. So please refer to this last book for a solved example. This book by Subramanian also gives a lot of insight, a lot of information, and it has a good chapter on the design of these RC walls. Okay. So please refer to these books for more information. So like yesterday, I must acknowledge certain people and institutes. So Department of Civil Engineering, Jabalpur Engineering College, it's very nice of them to organize and have this type of interaction. We look forward to more such interactions in future. Okay. So primarily the works which have been completed of Dr. Snehal Kaushik and Nishant Sharma, they have finished their works, and Somi's work is going on right now. So more other things we would like to learn from her. Although her name is not appearing here, but still things there. My another student is there, Navajit. He has started his work on seismic vulnerability assessment of shear wall buildings. So hopefully we'll learn more from him. And then, as usual, Professor Mukti taught me all these basic aspects of shear walls. My entire master's and PhD thesis were on different aspects of shear walls. So this subject is very close to my heart. And then we have the two organizations. One is NICE and IIT Guwahati. Their contributions are gratefully acknowledged. Okay. So thank you for the patient listening once more. Any
Thank you
questions?
very much, sir. So I request all the participants if they have any question they may ask. So actually a few questions came in chat box, so I will see and ask you.
Yes, yes, yes. Hopefully, I finished on time this
Yes,
time.
sir. Yes,
Phil?
sir. Yeah, yeah.
Okay. Yesterday, it slightly took more time.
Oh, no problem, sir. It was actually good. Mm. Sir, Vaibhav is asking how the tensile and compressive parameters determined for cyclic loading in FEA model.
Okay. So let me open that slide. Yes. So basically, when we are looking at these two damage parameters, DT and DC, okay. As I mentioned, these parameters uh, are not specifically fixed or calibrated for, say, column or wall or beam. Depending on the dimension, depending on the material properties, our numerical model needs to be validated. So you have the numerical model. You start off with some values of these parameters. Along with these damage parameters, there are other parameters also in CTP. So you start off with certain values of parameters, then try to match the stress distribution, the observed peak lateral strength, lateral deformation, the load deformation curve, different characteristics. You try to match with the original result. That may be an experimental result, that may be again a validated numerical result. Okay. So by virtue of that, by doing that, you have to change certain values of these parameters. May not be all, maybe for some of them. So you need to change these values. So by that way, you have to arrive at the values specifically for your model. Okay. So it may be for particular beam, particular column, particular wall. So there is no hard and fast rule that how to arrive at that. It is easier to do that calibration and fine tuning for monotonic analysis. For cyclic loading or cyclic analysis, it is more challenging. Okay. So my current student saw me, she spent a lot of time in playing around with those. Even in the monotonic analysis itself, there was a lot of playing around which had to be done.
Hello.
So yes,
So between the micro modeling, there are two models. One is elastic model and another is plastic model. So for
yes.
cyclic analysis, which model would you prefer?
See, if it is elastic model, that means your modulus of elasticity remains constant. So your load deformation curve will be a straight line. So if you do cyclic analysis with your elastic model, it will be tracing out only a straight line, right? Back and forth, right? It is elastic. And if you want to see the change in the stiffness, you want to see the damage, you want to see the degradation in strength, degradation in stiffness, that means you have to do nonlinear analysis, right? So in nonlinear analysis or inelastic analysis, you have to use that CTP. So there you cannot use a single value of your modulus of elasticity. You have to use the stress strain curve directly. Then only in the cyclic model you will get the pinching behavior, hysteresis behavior, all the loading, unloading phenomena, reloading phenomena. So all those characteristics will be only applicable if you use the nonlinear material properties. So in CTP, when you are using that plastic strain stress, that only is required.
Sir, in the elastic model, if we can include a damage parameter to reduce the stiffness of the material, so can it be used for cyclic analysis?
But in your elastic model, it will use a single value of stiffness. It will not change at every instant. Your curve will remain. If you change the stiffness, it will again show a straight line at a lower slope. The slope will change. but the cyclic nature will not be observed.
Okay, sir. So actually, I had a problem.
That's my knowledge as far as the abacus is concerned. I'm not sure that the option what you're talking about, whether that taken of nonlinear material properties or not. I don't think so. I'm not sure.
Okay. Actually, in the elastic model, I tried cyclic loading, but in the tension zone, the hysteresis curve is not properly formed. So I'm not sure about if I should use elastic model or plastic model.
But you are using this, then you have to use the plastic model, CTP model only, concrete damage plasticity model. You cannot use the elastic model.
Okay, sir. Thank you.
So one more question is there. Prajwal Pandey is asking, how can we do scaling of the wall? Like, do we need scaling of the walls?
For experimental work, I think.
Yeah, I hope so.
Okay. So scaling of any prototype to a model is based on certain calculations. Okay. So you may have heard about this particular theorem in fluid mechanics, Buckingham's pi theorem, right? You do some dimensional similitude analysis, right? So based on that, you have to carry out some scaling calculation. That's typically applicable when you do dynamic analysis. If you are doing dynamic experiment, a dynamic test, you have to use certain calculations. Okay, so you can refer to a book. There is one very good book. I'm forgetting the name on this experimental structural analysis. So that has a lot of that has extensive discussion how to do scaling of model. Okay, but then what happens is for when you do this nonlinear static analysis, cyclic loading or static testing. So there, what we do, we try to reduce the dimensions directly by 1/3, 1/4, 1/5, like that. Okay, but in some cases the reduction is not possible, like the diameter of bar. Okay, so from 20 diameter of bar, you cannot suddenly make a 4 diameter bar, right? So that is not practically possible. So I'm just forgetting the name of the author. There is a very good book where this scaling and other things can be done. Maybe who has asked the question can send me an email. I can have a look and tell you.
Okay, sir.
Yes.
Hello. Sir, Mahendra is asking, is shear wall beneficial in soft story RCC building?
Yes. In soft story RCC building, the reason why we are calling it as a soft story is that the stiffness is of the story is low as compared to the stiffness of other stories. That's how a soft story comes into picture, right? If the strength is low, it becomes a weak story. So a soft story building means the stiffness is low in one or more stories. That means when you have large earthquake shaking and lateral sway of the building, your displacements or deformations will be large, which will maybe detrimental, non-structural damage and other damages. So if you provide shear wall, RC wall, yes, definitely it will have the beneficial effect. In fact, one of the most popular retrofitting or strengthening method of open ground story building or any soft story building is by using reinforced concrete shear wall. So it is beneficial.
Okay. Mm-hmm. Sir, Ravi is, yeah, you may ask.
So in the finite element analysis, is it necessary for the full simulation to run, or can we use partial results also if the solution does not converge?
See, it all depends on what is actually you are looking for. Okay, so suppose you have the entire analysis. You have given, say, till a lateral displacement, say displacement control analysis, not the dynamic static analysis. Suppose you have given a displacement up to 100 millimeter. Okay, so now you expect that the model should run up to 100 millimeter. Now suppose it runs up to 45 millimeter. The basic phenomena what you're looking for, if you're looking at the initiation of first crack, okay, or first yielding of steel, right? So if those phenomena are observed before that 45 displacement is achieved, so between that 0 to 45 then your analysis is fine, that is sufficient. But if you are looking for a failure or degradation in strength or post peak behavior, okay, so at 100 you expect that the load deformation curve will reach the peak and then it will probably drop down, and then 45 probably still on the rising part. So if you want to look at that peak strength and post peak behavior, then your simulation is not sufficient. Okay, so what exactly you're looking for? So the early phenomena, first cracking, first yielding, two layers of boundary element reinforcement, initial spalling, so those may be observed before that 45 displacement. So if you are only concentrating on that part, probably your simulation is fine, it's sufficient.
So actually, in the elastic models, generally the simulation will run fully. But in the plastic models, there are sometimes issues in running the model. So should we change the parameters or consider it up to that only?
You have to change the parameters, right? You have to change the parameters, and then you are using you are writing your own program or using some available software or program.
So I'm using ANSYS.
ANSYS, okay. So in ANSYS, there must be certain parameters which, if you change, can probably give better convergence. I'm not sure about the accuracy, but definitely may give some better convergence. Generally, there are different tolerances, say for individual convergence, or say for individual iteration, or say for a slightly macro size loop. There are different tolerances. So if you can change those tolerances and reanalyze, probably you may get a better result. So it is always desirable you carry out the trial and error part as much as possible, and perhaps you can get in touch with some people who have analyzed such reinforced concrete components, not necessarily wall or other thing, in ANSYS. How do they tackle the tolerance? See, in elastic model, you are basically looking at only one slope or one stiffness, single value of E. There things are very much in control, very simpler. Okay, not many iterations are required, no change in stiffness. So things are pretty straightforward. But then any type of inelastic or nonlinear model, things go out of control.
Okay, sir. Thank you.
So one more question. Ravi is asking, is it comparable that if we use this infill wall in place of this shear wall, because infill wall also provide great stiffness?
See, the behavior of infill wall and shear wall, the behaviors are different, because infill wall has different modes of failure. Like infill wall is strong in taking compression, but weak in taking tension. If you are using the masonry walls, say brick or AC block or whatever, you have certain weak portions like bed joints and other locations. You have cracks coming up very early. So lateral strength taken by the infill wall and their failures, they are different from that of shear wall. So in general, strong
Hello, sir. Use
Am I audible?
yeah. Now you are audible, sir.
So in general, if you directly compare, shear walls are shear walls are better than walls, because in out of plane direction, masonry walls will fail earlier than the shear walls, right? Because you provide a shear wall and a masonry wall, you never know that in which way the right.
Hello. Hello, sir. Your voice was
Yes.
breaking actually.
Hello.
Yes, sir.
Hello. And
Yeah, it is
so
coming now, sir. Yeah.
towards the end was and all is
So it is
shear
still
wall.
breaking, sir.
Okay, so wait for 1 minute.
Yeah. Sir, I will ask him to email you questions, so you may answer
Yes,
there
yes, yes,
also. Yeah.
yes, yes. I think
So yeah,
yes.
yeah. Okay. So thank you very much, sir, for such an informative session, and thank you all the participants
Okay.
also for joining us. Okay, sir. Thank you.